Swayam Prabha. Digital India. Educated India.
So if I can write down that del square psi equals to 0, my equation is nothing but dou square psi by dou x square plus dou square psi by dou y square equals to 0. Now this has to satisfy, this has to be satisfied. If you want to satisfy this, let us see how this is actually satisfying the irrotationality condition. So that means same Laplace equation in terms of psi I should be able to get from my equation which I have written for rotation. How do I find out the rotation for xy plane? I will write down the rotation as omega z. So if I write down omega z is nothing but 1 by 2 dou v by dou x minus dou u by dou y. So in this, if I substitute the value of v and u in terms of psi, I will be able to write down 1 by 2 multiplied by minus dou by dou x, dou psi by dou x, minus dou by dou y, dou psi by dou y. Alright? And that is equals to minus 1 by 2 dou square psi by dou x square plus dou square psi by dou y square. And this is minus 1 by 2 is constant, it can be taken out. So finally, I have the expression dou square psi by dou x square plus dou square psi by dou y square. So that is nothing but my Laplace equation, and that should be equals to 0. So if you satisfy the Laplace equation using psi function, that indicates that you are satisfying the irrotationality condition. Okay. So there are certain properties of the psi function. Let us look at that. The psi function, or which is a function in space and time. So we are telling that okay, in all through phi function and psi function, we have not used the function here. When we write only psi of x, y, and we don't write t, because always we look at these functions at a particular time, at one time instant. So we are taking the time out. So if I move from one time instant to next time instant, then again my psi function is going to be possibly different, and at that time it is again a function of x and y. So we are looking at the function in terms of x and y only. So psi xy, if it is constant, if let us say psi function is something like x square plus y square minus 2xy or something, so that is equals to some constant c1, then that is going to represent one equation of a streamline, or that will represent one streamline. And same equation, if I equate it to some other constant, let us say c2, it will show me another streamline. And similarly, if I start equating that to different constants, I will get different streamlines or a set of streamlines. Okay, so these streamlines, which are also called as flow lines. So basically, it is showing me that this is one flow line. If constant 2, then that is another flow line. If it is equated to constant 3, this is another flow line. Okay, so these are the properties. Similarly, psi function, as we have already discussed, it is going to exist both for rotational as well as irrotational flows. And when the flow is irrotational, the psi function has to satisfy the Laplace equation, that is del square psi equals to 0. All right. Now there is another property of this psi functions or psi lines that's very important. When you have different psi lines, you can actually find out the discharge through two psi lines or streamlines. Okay, so the discharge between two streamlines, streamline 1 and streamline 2, is going to be equals to the difference between the values of these psi functions. Okay, so I have, let us say, the psi function for the streamline 1 and for 2. If I evaluate what are the values, then I find out the difference. That difference gives me the discharge between these two streamlines. Let us try to understand that with a simple figure. So I have psi 1 and psi 2. Let me say this is another figure where I have psi and this another line which is the elemental difference, which is psi plus del psi. Okay, and I have this chord which is moving from A to C. And if I write down like this A, B, C. So these are the horizontal projection AB and vertical projection BC. So through this, the flow is taking place. Okay. So if we write down the flux through BC, it is nothing but my U dy, isn't it? So the distance in the y direction is delta y and velocity is u. The flux is u dy. Similarly, the flux through this face, that is AB, is going to be minus v dx. Minus v because it is in the reverse direction of y. Okay. So I have this u dy minus v dx. And if you look at our basic equation for the stream function but in 2D, we have already written earlier. If you see, that is nothing but your dou y by dou x is equals to v by u, which is basically slope of the stream function, isn't it? So if I write down, you can see here, it will give me u dy minus v dx will be equals to 0. All right. So if it is not equals to 0, then obviously there is some flow, right? So I can write down the discharge dq through this elemental streamline increase or two streamlines, that is psi and psi plus dou psi. The discharge is going to be dq, that I can write down as minus v dx plus u dy is equals to d psi. Okay, so I can write down this v is equals to dou psi by dou x into dx plus dou psi by dou y into dy. And if you see here, this dx cancels out, dy cancels out, then finally I'll get only d psi. So here the multiplication of 2 doesn't matter because this is only elemental. So I'll get only d psi. Alright. So dq or the discharge through two streamlines can be obtained, and which is nothing but the difference between the two stream lines, okay, or values of the two streamlines. So I can integrate this and I can find out that if dq is equals to d psi, q is equals to integration from psi 1 to psi 2 d psi, and then I will be able to write down psi 2 minus psi 1 is nothing but my discharge q. All right. So you can find out the discharge between two streamlines by taking the difference between the values of these two stream functions. All right. So this is a property which you can use very well in fluid kinematics. So again, when I'm talking about fluid kinematics, just to repeat that all through we have not been discussing about the forces. We are only talking about the fluid motion. Okay. So that is what is your fluid kinematics. All right. Now let us look at the next concept, that is flow net. So when I am talking about flow net, before I understand the flow net, let me understand what is equipotential line. I have already discussed slightly earlier that when you take phi xy, phi function, and equate that to a constant, you get a line, and that represents your equipotential line. Okay. So if phi xy is constant, what will happen to dou phi? Dou phi is going to be 0. All right. So now if dou phi is 0, I know phi is a function of x and y. If I write the partial derivative of that, I can write down dou phi is equals to dou phi by dou x dx plus dou phi by dou y dy. And we already know dou phi by dou x is minus u and dou phi by dou y is minus v. So I can write down minus u dx minus v dy is equals to, or that implies dou y by dou x, if this is equal to 0, I can write down dou y by dou x is equals to minus u by v. All right. So similarly, now if I want to write down the psi function, and that is equated to the constant, that is going to give me the streamline or flow line. So similarly, psi xy is constant, represents a streamline, and if I take the dou psi, then that will become 0. And if I write down the expression for the dou psi again, I can write down like this, substituting the values for dou psi by dou x and dou psi by dou y. I can write down the expression minus v dx plus u dy. That implies dou y by dou x is equals to v by u. All right. Now you look at these two. So one is here dou psi by dou x is equals to minus u by v, and another is here dou y by dou x equals to v by u. If we know that these are two different lines, equipotential line and streamline, now let us take the product of these two lines. What will happen to the product of these two lines? They will give you a value equals to minus 1. The product of the slopes of phi and psi lines is going to give you minus 1. And mathematically, what is the property of that? Property, we know that these lines are orthogonal to each other, or they are perpendicular to each other. So phi and psi lines are orthogonal in nature. Okay. So if you know phi line and you draw a perpendicular line to that, that represents your psi line. Okay. And if you have a psi line and you draw a perpendicular line to that, it represents your phi line, vice versa. Okay. So these lines constitute to form the flow net. So typically, this is how it will look like. If you have, I have shown you straight lines, but not necessarily it will be straight lines. It could be a curved line also. So you have the psi lines here, and the phi lines are going to be perpendicular to that. All right, and this represent your solution of Laplace equation. So a flow net, which is a combination of phi and psi lines, are nothing but a solution of Laplace equation for a particular problem. If for a problem you are solving and you could draw the phi lines, you could draw the psi lines, then that indirectly represents the solution of the Laplace equation for that flow problem. All right. And as I was telling, these lines, just to make sure that you don't misunderstand things, I may have the psi lines like this. Okay. So if I have psi lines like this, then by freehand, I'm trying to draw, may not be necessarily correct. So this is my phi line. Then if I draw here, this could be my phi line. If I draw here, this could be my phi line. So always phi lines are perpendicular to the psi lines at the intersection. When they intersect each other, they have to be perpendicular. Okay, that's the property you have already seen. So there are ways. Earlier it used to be applied quite a lot, but nowadays with the development of numerical models and computational facilities, there are not a lot of numerical models we are doing a job, but we need to understand the properties and its usefulness. All right. So now let us look at some other properties of flow net. So the velocity field is determined from continuity equation and the condition of irrotationality. So knowing the velocity field, the pressure field can be obtained from the Bernoulli's equation. So Bernoulli's equation, which we will be studying at a later stage, but this Bernoulli's equation is going to relate the pressure field as well as the velocity field at one point to the pressure and velocity at the other point. So if I know the pressure and velocity at one point, and if I know the velocity at other point, I can find out the pressure at that point. So vice versa. If we know the velocity field all through, then it's easier to derive the pressure field from this. So from this equations, from the psi function and phi function, we can find out what are the velocity fields, and we can derive the pressure field based on that. Next property is very important property, which is property of superposition. So it says the functions that individually satisfy the Laplace equation may be added together to describe a complex flow problem. And let us say I have a domain which is slightly complex. I can divide the flow domain to different domains. Let us say I have some domain, something like this. Okay, within that I have some kind of circle like this. This represents, let us say, one of my lake, and this represents that there is a small island within the lake. Now I want to understand how the flow is going to take place. If I am solving for phi function, I will use the phi function first to solve the flow completely in the domain that is here, rectangle. Okay, so I have a phi function, let us say that is phi1. Okay, and now for the circular domain, that's the island, I will again solve the phi function and I will find this is my phi function for the circular domain. Okay, this may be phi2. Okay, so if I take phi1 minus phi2, basically I am subtracting the island, so my island is not there. So if I use phi1 minus phi2 and then solve, get the solution for that, that gives me the solution for the flow domain. Okay, so that is the advantage. Instead of taking the complex shape and this geometry, you can split it into different geometries and superpose that to get a solution which is still going to be the same. So phi or psi function are going to satisfy the same flow problem. If phi1 and phi2 are satisfying the Laplace equation, then phi1 minus phi2 will also satisfy the Laplace equation. All right. Okay, so this is an example of the streamlines and potential lines or equipotential lines. You can see here this is a dam, and on one side you have some mass of water which is standing, and when the dam is holding this mass of water, there could be some amount of water which will try to seep through this dam. If it is an earth dam, there is a permeability or there can be some flow through this dam, which may be very minor, but still we want to find out how much flow can take place and how it is going to take place. These are very critical. Okay, so these are the lines that we can plot typically, which shows you the streamlines or flow lines. And you see here, these are the lines which are going perpendicular to the streamlines. This shows you the equipotential lines. Okay, so you can find out the characteristic and how the flow net looks like. And what is the advantage here? If you look at this streamline, they are quite spacing, or the spacing is quite larger or spacious at this location. But as they flow and come towards this, the spacing is less. So what does it mean? It means that the kind of flow, we know that property, the discharge between two streamlines is your difference between the values or values obtained for the streamlines, let us say psi1 and psi2. Okay, so the psi1 and minus psi2 or psi2 minus psi1 is going to be constant all through. So whatever discharge is coming through this is going to also pass through this. And we have also seen another property, there cannot be any cross flow across the streamlines. So the discharge that is coming through this is passing here. So if the discharge is same, we know that this is a larger area or width and this is a lesser width. So same discharge passing through a lesser width will result in higher velocity. So if we see that the streamlines are very closer, then that indicates that the velocity is higher at those locations compared to another location where the same streamline is having more space or more distance between them. Okay, so these are a couple of properties which you can quickly understand by just looking at the flow net. So there are a lot of advantages of having this kind of lines. All right. So now let us quickly look at some other aspects of that. There exists an interrelationship between the phi and psi functions. So we have already seen that if you know that there is a phi function, you can correlate that to the velocities, and again the same velocity is related to the psi function. So if you know phi function, you can find out psi function. If you know psi function, you can find out phi function, or vice versa. All right. So let us quickly look at one example of that. Let us say I have the psi function which is psi equals to 2xy. So you have to find out the phi function, that is potential function. So how do I do it? I know psi is equals to 2xy, and I can write down u is equals to dou psi by dou y. That will give me 2x, and I can write down v is equals to minus dou psi by dou x. Please remember we have this minus sign here. V is equals to minus dou psi by dou x. that is equals to minus 2y. All right. So now I have u and v. Can I not take this u and v and find out my phi function? So if I know that the gradient, negative gradient in any direction gives me the velocity in that direction. So let us say my velocity in the x direction is u. So I know dou minus dou phi by dou x is u. So I'll equate that. If I equate that, I'll get it. But now before that, I think I have shown here the resultant velocity can be written like this: 2x I cap minus 2y j cap is equals to the resultant velocity. And I can write down in quantitative term if I want to evaluate u square plus v square uh, square root of u square plus v square equals to the resultant velocity. That I can find out. So that is not difficult as you know that. Now let us see, as I was discussing, to find out the phi function. So if I equate that, dou phi by minus dou phi by dou x is equals to u, that is equals to 2x. Now from this, if I integrate, I can find out what is the value of phi. So if I integrate, I will be able to write down minus x square plus fy. Fy is a constant. So even if you integrate, you will get a constant. And in this case, the constant can be a function of y only, right? Because you are having x direction, the constant can be, possibly can be a function of y. So now let us look at the other velocity, that is v, and equate, and we can find out another phi function when we solve the equation for dou phi by dou y equals to v, and that is going to give us phi equals to y square plus f of x, or it could be a function of x. Now we know that the phi function is single phi function, it is not two. So the total phi function, when you want to derive, what you need to do, you have to add these two. So what will happen? The phi is equals to minus x square plus y square. So you got minus x square from here plus y square from here. So if you add these two, you will get minus x square plus y square. So now we have seen here, we said that it may be a function of y, or it can be a function of y. Here we are telling it can be a function of x. But when you add together, that constant has to disappear. So it cannot be a function of x or y. So finally, the phi is nothing but minus x square plus y square. This is your phi function. So similarly, if you have been given a phi function, you should be able to derive what is the psi function. And there is a trick here that you should also understand. Let us say this function, I don't know what will be this function here for that, but let us say this function is going to be minus x square, let us say plus 2xy, okay, plus a function of y. Here again y square, again plus 2xy plus f of x. Then this function will become minus x square plus y square plus 2xy. Okay. So if there are terms that are appearing in both the cases, you should not add it together. This has to come only from one case. So either from here or here. So it will appear only once. You should not add and make it 4xy. That's wrong. Okay. That will give you a completely wrong value. So this is something you have to remember and you have to do when you are applying this. All right. Okay. So now let us quickly look at a couple of more examples and we will be able to understand and appreciate more. This is an example which says a two-dimensional stream function of a flow is given here, that is as a psi function. The question is the flow irrotational? And next is estimate the discharge per unit depth passing across a line joining 2 points, that is point 11 and point 15. So first point is going through 11, second streamline goes through 1.5, 1.5. These are the spatial xy coordinates that are given. Okay. Now first let us see the solution. You have been given the psi function, that is 3 plus 6x plus minus 4y plus 7xy. Okay. So now this function, once you have been given, first thing that you have to find out whether the flow exists. So how do you find it out? You have to calculate the or apply this psi function to the continuity equation, isn't it? So if you find out the value of u and value of v and then substitute here, you should be able to get a value of 0. Then only you can say that the continuity equation is satisfied and this psi function says that the flow will exist. So first the flow has to exist. Okay. So if you look at the second order terms are not there in the equation. Okay, so here you don't have any second order term. So when you take the u, this let us say I'll find out u here. So if I try to say u is nothing but my dou psi by dou y. So dou psi by dou y, you will get minus 4 plus 7x, isn't it? And when you take minus 4 plus 7x and then take dou u by dou x, you will get a value possibly only 7. So from here, if you find out the u and v, you will get and the uv and substitute here, that will become equal to 0, and that says that this satisfies the continuity equation. And once this satisfies the continuity equation, then you next you have to find out the first question, that is if the flow is rotational or irrotational. Okay, so to get that, we have already seen either you can satisfy the rotational equation, you find out omega z, or you apply that to Laplace equation. So if you want to apply that to Laplace equation, that is dou square phi by dou x square plus dou square phi psi by dou y square equals to 0. So when you apply that, you see the psi function does not have any second order term, and when you are taking the derivative, second order derivative, then obviously this will disappear. Okay, so it will become 0. Okay, both continuity equation and irrotational condition are satisfied, so the flow is irrotational. Now let us look at the next question, next part of the question, that is estimate the discharge per unit depth. Now what is the discharge? We know that the discharge between 2 points is, let us say, psi 2 minus psi 1. So I have point 1 and point 2. The line passing through point 2 is psi 2. The line passing through point 1 is psi 1. And if I take the difference, then I will get the discharge. So first, if I want to evaluate what is psi 1, that is the line passing through point 1, 1. So this is my equation. And if I want to substitute the value of x and y, I will be able to get psi 1 at 0.11 equals to this. So I have just substituted the values of x and y at the respective places. Okay, and that gives me the value as 12, which is 12 meters square per second. Let us say I have units or dimensions are in meters and time in seconds, so it gives me the value as 12 meters square per second. So similarly, if I find out psi 2, that is going to give me 21.75 meters square per second. Now, what is my discharge through these two streamlines? The discharge is difference between these two, psi 2 minus psi 1. That is 9.75 meters square per second. And this is the value for unit depth. So I have two streamlines. Let us say I am looking at a river flow from the top. So I have two streamlines. So between these two streamlines, this is the discharge that I could obtain. That is for unit depth. Now, if I have a depth of, let us say, 10 meters, and all these flow conditions are uniform across along the depth, there is no variation along the depth, then I can multiply the depth of 10 meters and I can get a value. Okay, so this is how you can find out the discharges between two streamlines. All right, let us quickly look at another example. We have already seen in the previous lecture that there is a circulation which can occur, and you can find out the circulation by taking the integration about a closed curve, integration of the velocity about the closed curve. Okay, so now the problem says there is a flow around a cylinder with a circulation of 400 meters square per second. Now, neglecting all viscous and compressibility effects, determine the velocity on the surface of the cylinder. So the question says there is a cylinder and there is a circulation around that, and the value of circulation is given. Now, what you know that circulation is a integration of velocity around that line. So if you want to write it down, the velocity on the surface of the cylinder due to circulation alone, because we are neglecting all other effects, due to the circulation alone, we can write down as this. Circulation, that is capital gamma, is equals to 2 pi r is the circumference, and integration of the velocity along the circumference, let us say Vc. And because this is cylinder and there is going to be a constant velocity at all the points, so it is considered as Vc. And if we write down this expression, then our job is easy. Okay, so we can write down Vc is equals to gamma by 2 pi r. Now here, I think in the problem I have forgotten to give the radius of the cylinder, so that is given as 0.6 meters. So if it is 0.6 meters, then obviously you will have the value of the velocity Vc equals to 106.1 meter per second. So if you have the circulation, you can find out the velocity around the cylinder also. So these are various applications and quick examples that you can go through, and you have a lot of other example problems that you can also solve to understand the subject more. So with this, we have come to the end of the fluid kinematics, and we have understood all the subjects. So now in the next lecture, we'll start fluid dynamics. Okay. Thank you so much.